get started, I'm going to be talking about HF propagation, particularly with cycle 25. And I thought that it would be apropos for us to go over and remember what radio waves are. Okay, let's think about what radio waves are. Can anybody tell me what radio waves are? Anybody? Well, they're waves, so they're sort of sine waves, and they are electromagnetic energy. Electromagnetic energy that we're throwing up out into the atmosphere, and on HF, they're going to hit the ionosphere and come back down. So I wanted to make a demonstration of electromagnetic energy. I've got stuff here. So I've got two conduits. I've got a piece of copper pipe, just standard copper pipe, and a piece of PVC pipe. And I've got a marble, okay, just a plain marble. Hook, if I could get you to come over and help me, we can be seen here. I want you to hold this piece of PVC pipe and put your hand underneath here. I'm going to let the PVC pipe go. I'm going to let it go. Now the marble comes, or the magnet comes right through. Right here, as soon as I let it go, I'll open my hand up. Comes right through, okay? Set that down over there. Now, this is copper. And would you agree that that's not sticking there at all?
Nope.
Okay. So you don't even need to do that. I'm going to let it go. Then reach under here. Took that long to fall out. Let's watch that again. Here's the magnet in the copper. It's not sticking to the copper. Let it go. Then reach down here. Now it fell through. What made it slow down that way? What made it? Electromagnetic energy. So the magnet is not attached, is not attracted to the copper at all. As it travels through the copper, the magnetic field generates an electric field. The electric field recreates a magnetic field that slows down the falling of the magnet. So I'm going to come up here again, watch it. I let it go. And you saw how long it took to fall through. Pretty cool, huh? So that's electromagnetic energy. That's what we're going to be talking about. That's what we're sending out via our radios to the ionosphere. So let me share my screen and start our slideshow. So this is actually the lecture that I will be giving next week to the general class radio class. We're going to be talking about the ionosphere. We will talk about the sun, and we'll talk about propagation, prediction, and how we're doing it. So the ionosphere starts about 30 miles above the Earth and it extends to about 300 miles. In fact, the International Space Station is right in the middle of the ionosphere. What is about 160 or 200 miles up? So at that point, the air is thin enough that ultraviolet radiation can break the molecules apart. So if you know, our atmosphere is made of 79% nitrogen, 21% oxygen, and then a bunch of minor gases that are in the background. But when you get further and further away from the surface of the Earth, the gas molecules get further and further and further apart. Then you've got ultraviolet radiation that comes in from the sun. That ultraviolet radiation hits one of the gas molecules and it splits an electron off from the gas molecule. And so now you've got a positively charged gas molecule and an electron that are floating up there. They are so far apart when you get anywhere from 30 to 300 miles above the atmosphere that it takes a while for them to reconnect with each other. And so what happens is you ionize the gas. You create ions. You create a positive side and a negative side. And those ions act just like conductors, just like the conductors of this copper pipe, just like the copper pipe that we drop the magnet through. And we can use that electromagnetic energy as it goes through the ionosphere. It will get refracted and bent back to the Earth. And that's how we're able to have shortwave communication. And there are 3 layers of the ionosphere. We've got the D layer, the E layer and the F layer, and the F layer splits into two sections when the sun is hitting it. The D layer is the lowest layer closest to the Earth at about 30 miles. The F layer is highest between 200 and 300 miles. The E layer is in between those two. And you'll notice that the D layer is only present when the sun is hitting it. And as soon as the sun stops hitting it, the D layer goes away really quickly. Same thing for the E layer, it lasts a little bit longer. And the F layer, when the sun is hitting it, it splits into two portions, the F1, which is lower, and the F2, which is higher. And then at night, the F layer combines into a single layer here at night. So the D layer is 30 to 60 miles in atmosphere in altitude, and it's only present when it's illuminated by the sun. And I like to think about the D layer. The D layer is a bad layer. It absorbs our signals. So I think about that darn D layer. That darn D layer helps ruin propagation because it completely absorbs our signals. It disappears at night. So as soon as the sun hits it, the D layer appears, and the sun goes away, the D layer disappears. The E layer is a little bit higher, and it lasts just a little bit longer, but it disappears at night as well. And sometimes the E layer will enhance propagation on the higher frequencies. On the lower frequencies in HF world, it tends to not be helpful. It tends to absorb the signal. No, we'll talk about the gray line here in a minute. That's a great question. So there was a question about the gray line, and we'll talk about that in a minute. So the F layer is 100 to 300 miles above the Earth. During the day, it breaks into the F1 layer and F2 layer. And at night, it returns into a single layer. And these layers vary with local time, your latitude, and the amount of solar activity. The stronger the illumination from the sun, the higher the F2 layer will be. And if you think about that, the higher the F2 level is, the longer your hops are going to be from the Earth to the ionosphere and back down. So the ionosphere, because it is charged, it has positive and negative charges, it's able to bend or refract radio waves depending upon how strong the ionosphere is ionized. The stronger the ionization, the higher the bending. The other thing to keep in mind is that the higher the frequency, then the less bending there is. So let's talk about frequency. Like our 2-meter frequencies, the 140 megahertz, that's much higher than 20 meters, which is 14 megahertz, okay? So 140 megahertz is a very high frequency. 14 megahertz is a high frequency, not very high, it's a high frequency. But if you think about it, the 2-meter band, the peak to trough of the sine waves are only 6 feet across, 2 meters. The peak of trough of the 20-meter band is 20 meters across, or 66 feet, right? And so remember, these molecules high in the ionosphere are really, really far apart. So at 200 miles above the Earth, these ions are really separated and they can't come back together quickly. At 30 miles above the Earth, they're much closer and they get attracted and they come back together much more quickly. Does that make sense? So the very high frequencies, like 2 meters, 140 megahertz, actually will punch all the way through all of the layers of the ionosphere because their wavelength is short enough that they'll go right through. The lower frequencies, say 14 megahertz, are going to get up there and they'll tend to run into some of those ions and get refracted or bent back to Earth. Does that make sense? So VHF and UHF are hardly bent. They tend to go in a straight line and just keep going. So there's a couple of things for us to think about. The critical angle is the highest angle at which a radio wave will be refracted back to Earth. So let's say I'm talking about 20 meters, which is 14 megahertz. the critical angle there may be something like 60 degrees. So if I aim my radio wave 60 degrees above the horizon, it will get reflected. If I aim it at 70 degrees above the horizon, it's not going to be reflected. It will punch right through the ionosphere. And the critical frequency is the frequency that will be reflected if I send it straight up. And this you can look at with solar prediction patterns, solar weather. We can find out what our critical frequency is at any point on the Earth. And so generally the critical frequency is going to be somewhere below 7 megahertz. So if I send a signal straight up, if I'm higher than 7 megahertz, say 8, 9, 10 megahertz, it's going to tend to punch right through. Sometimes if the ionization is high enough, then 7 megahertz or 40 meters will be reflected straight down. The other thing we have to keep in mind is absorption, that darn D layer. The D layer will absorb our signals, particularly below 10 megahertz. So that's why 80 meters and 40 meters, as 3.5 megahertz and 7 megahertz, are not good for DX during the day. They tend to get absorbed by that darn D layer. But at night, the D layer goes away. And so 3.5 megahertz and 7 megahertz can start bouncing around the Earth by bouncing off of the F layer. Does that make sense to everybody? So let's take a look at this. So here I've got my transmitter, and let's suppose this is the critical angle right here for the frequency that I'm using. And remember, the critical angle is going to be dependent upon the frequency. So if I'm at VHF frequencies, there is no critical angle. The energy is all going to punch right through the ionosphere. At 14 megahertz, say on 20 meters, the critical angle may be like 45 degrees. So at 45 degrees, my signal will go up and it will be refracted by the ionosphere and then come back down. Anything lower than the critical angle will go further out and bounce back down. Okay? So this is one reason why when I want to work DX, I want to have an antenna that has a low takeoff angle. So a dipole has a takeoff angle of about 30 degrees. So a dipole that's about half a wavelength above the ground has a takeoff angle of 30 degrees above the horizon. A vertical has a takeoff angle of about 17 degrees. So the dipole would tend to have this takeoff angle, say right here, and a single hop would put me down at this point, where a vertical would have a takeoff angle about here, and a single hop would bring me down at that point, much further away. Does that make sense? Okay. Now, at some point when I get above the critical angle, which for this frequency will be this, if I shoot my angle up any further than that, it's not going to be refracted, and it will just disappear off into space to travel forever at the speed of light until some other civilization picks us up and goes, what are these people talking about? QRZ, QRZ. What does that mean?
Hey, Tim.
Okay. So a hop is a single reflection from the ionosphere. A hop is a single bounce. And a skip, which is our skywave propagation, which is what we use for shortwave or HF communication, it represents refraction from the highest level of the ionosphere. The higher the reflecting lesion, the longer the hop. Does that make sense? So the F2 layer will give us hops up to 2,500 miles in length. The E layer, because it's lower, will give us hops of about 1,200 miles in length. Now, sometimes you will have multi-hops. The ocean is an excellent conductor because it's salt water, and frequently my signal will go up to the ionosphere, come back down, bounce back up to the ionosphere and back down. In fact, sometimes they can take 6 or 7 hops between the Earth and the ionosphere to get from my station to a station on the other side of the world. It may take up to 7 hops, and that happens pretty frequently. Another term that we need to understand is maximal usable frequency, or MUF. And it is the highest frequency at which skywave propagation can occur between 2 points. So if I take a look and want to talk to my friend Jose in Spain, I can use propagation predicting software to tell me at this particular time of the day, with the sun at this particular level, this is the highest frequency I can use to get from Nashville, Tennessee to Zaragoza City, Spain. That's the maximum usable frequency. If I go higher than the maximum usable frequency, what happens to my radio wave? It goes right through the ionosphere. Anything lower than the maximum usable frequency will be transmitted unless it gets absorbed by the darn D layer. And that's where we talk about the LUF, the lowest usable frequency. So there is a sweet spot, that just right point where you're above the lowest usable frequency and below the maximum usable frequency, that your HF signal will bounce off of the ionosphere and get from point A to point B. If your signal is below the lowest usable frequency, what's happening to it? No, below the lowest usable frequency, it gets absorbed by the D layer. It gets absorbed by the darn D layer. So you've got to pick the right frequency that will punch through the D layer, or wait until the D layer goes away at night. And it's got to be below the maximum usable frequency in order to be reflected. Otherwise, it will punch through the ionosphere. Does that make sense? Now, there may come a point when the maximum usable frequency is less than the lowest usable frequency. And when that happens, you are not going to be able to contact the patient, or your patient. We talk about doctors. Not going to be able to contact your communication partner by skywave propagation. So when we can't use skywave propagation, we may use a couple of other forms of propagation. One of them is ground wave propagation. In that, our radio waves travel across the surface of the Earth. They do not go nearly as far. And the higher your frequency is, the less ground wave propagation you have. So on 10 meters, 28 megahertz, I may have ground wave propagation out to about 10 miles. On 80 meters, I may have ground wave propagation out to about 75 to 100 miles. So I want everybody to think about our alternates that we've used on the Tuesday night nets. Sometimes we've used 10-meter alternate, sometimes we used 80-meter alternates. And we're much more likely to hear everybody on 80 meters using ground wave propagation. And then there's also another propagation we'll talk about when I get to antennas. I'll be talking about near vertical incidence skywave propagation. We'll talk about that in a minute. But ground wave propagation is propagation along the Earth's surface, high frequencies like 10 meters, 20 meters, don't go as far as low frequencies like 80 meters or 40 meters, okay? The other thing to keep in mind is the Earth is a sphere, and your waves, your propagation goes all the way around the sphere. And if I'm using a dipole antenna or a vertical antenna, an antenna without directivity, then I'm transmitting in a forward and backward direction. So if I think about the short path, that is the shortest distance between my station and the station I'm trying to contact around the sphere. But there's also, if you go 180 degrees in the opposite direction, that's what we call the long path. Sometimes your signal goes around both paths, and you can hear yourself with an echo with a delay of about 1/7 of a second. And so the distance all the way around the Earth takes about 1/7 of a second at the speed of light and the reflections. So has anybody heard their own reflection? Yeah, Gene's saying yeah. So I mean, I've heard mine. It's kind of weird. You're talking and you're listening on the monitor, and you hear it kind of split up like it's just a tiny bit of a blurry reflection of your signal. Pretty cool. Okay, so I'm going to have some questions. Y'all didn't know there was going to be a test, did you? Okay, well, let's see how well you did. How is a directional antenna pointed when making a long path contact with another station? Do we point it towards the rising sun? Do we point it along the gray line? And Paul, I'm going to talk about gray line when we finish this question. Do we point it 180 degrees from its short path or towards the north? C. Yeah, 180 degrees from its short path heading. So let's talk about the gray line. The gray line is that portion of the Earth that is partly in sun, partly in shade. And you get really good propagation on two different stations that are on the same part of the gray line, primarily because the D layer really quickly falls apart and the F layer is still really highly ionized. So when the F layer gets into dark, it's not ionized as much. So the D layer falls apart before the F layer does. So on the gray line, the D layer has disappeared, but the F layer is still very highly ionized. So you get incredibly good refraction along the gray line. Does that make sense? And so if your station and the receiving station are both on the gray line, you can get amazing propagation for the 10 or 15 minute period that you're in the gray line.
So
yes.
You're in a helicopter,
The gray, you could actually, yeah, you stay real well if you were in a helicopter or a jet plane. Helicopter is probably not fast enough to do it, but a jet plane probably would be. All right, let's get another question. How might a skywave signal sound if it arrives at your receiver by both the short path and long path propagation? Well, how about D? A well-defined echo might be heard. What usually happens to radio waves with frequencies below the maximum usable frequency and above the lowest usable frequency when they are sent into the ionosphere? Exactly, they're bent back to the Earth, which is what we want. What is the approximate maximum distance along the Earth's surface that is normally covered in a single hop in the F2 region? Yeah, 2,500 miles. 1,200 miles would be the E layer or D layer, the E layer. Oh, there you are. So I just came up with that one with the E layer.
asked and answered.
Asked and answered, yep. Which ionospheric layer is closest to the surface of the Earth? That darn D layer, right? Where on Earth do ionospheric layers reach their maximum height? When the sun is overhead, when the sun is just set, when it's rising, or when the sun is on the opposite side of the Earth? A, when the sun is overhead. So when it's directly overhead, you're going to have the maximum ionization. Makes sense, right? Why is the F2 region mainly responsible for the longest distance radio wave propagation? Why is the F2 layer responsible for the longest? It's because it's the highest. It's the highest ionospheric region. That makes sense, doesn't it?
Yep.
Okay. What does the term critical angle mean when we talk about radio wave propagation? What is critical angle?
D.
Exactly. The highest takeoff angle that will return a radio wave to the Earth under specific ionospheric conditions. Why is long distance communication in 40, 60, 80, and 160 meter band more difficult during the day?
C.
That darn D layer, right? That D layer really shoots us down. Which ionospheric layer is the most absorbent of long skip signals during daylight hours on frequencies below 10 megahertz? D. The D layer. Okay, are y'all still able to hear me? Wave if you can. Perfect. Okay. So now let's talk about the sun, because the sun is what gives us that ionization that we need. So the sunspots occur in an 11-year cycle. And I think Jeff mentioned that we're at the beginning of cycle 25, which is good news. And these are old slides, but I got a slide of the current sunspot cycle to take a look at. So sunspots represent the number of sunspots in groups at any given time. And the sunspot number is very useful in assessing overall solar activity. Now, about 4 years ago, we were dealing with sunspot numbers of 0 and 1, and propagation was pretty bad. The more sunspots there are, the higher the ultraviolet radiation is. The more ultraviolet radiation that gets generated, there's better ionization and improved propagation on the HF bands and possibly even into the lower VHF bands, like 6 meters. 6 meters. Higher sunspot numbers mean poor conditions on the 80 and 40 meter band. Why? More ionization of the D layer, so you get more absorption, except at night. So at night, you get good propagation because the F layer has been highly ionized. Lower sunspot numbers mean poor propagation on the higher frequencies, 10 meters, 12 meters, 15 meters. They are now starting to come alive, though. I was listening to 10 meters just earlier this week, and I was hearing stations coming in from Japan, which is pretty exciting. Hey, Peter, hello in Japan, because he's konnichiwa. The 20 meter band is usually good regardless of the sunspot number. So 20 meters is sort of our workhorse band for HF propagation. Now, one thing to keep in mind is that the sun rotates around its axis every 28 days, and therefore sunspots tend to reappear if they're still present, and HF propagation tends to repeat itself in 28-day cycles. So whatever is happening today is pretty similar to what will happen 28 days from now. So here is an older sunspot schedule, and I've got a newer one I'll show you here in a minute, but this ended up in January of 2008. So this was cycle 23. And if we take a look at daytime and nighttime propagation is best on 160 meter, 80 meter, and 60 meters. Evening propagation on 30 and 40 meters. 20 and 17 meters can tend to give us propagation almost anytime. And then only during the daytime do we have good propagation unless the sunspot number is really high on the high bands, 10 meters, 15 meters, and 12 meters. Now, 10 meters is often used for local communication 24 hours a day. What sort of propagation would that be? Ground wave propagation, exactly. All right, so how do we measure solar activity? Well, one measure of solar activity is the solar flux index. It's the amount of 2,800 megahertz energy coming from the sun. And this is reported on solar weather reporting websites. If you go to QRZ.com, there's a solar predictor or a solar reporter right there, and I'll show you that in a minute. The K index is another thing that we'll look at, which is the short-term stability of the Earth's magnetic field, and it's reported every 3 hours from NOAA and WWV in Fort Collins, Colorado. And then the A index is the average of the previous 12 K indices. So the K index goes from 0 to 9. 0 is very quiet. 9 is an extreme geomagnetic storm, which will affect propagation in the way that the ionosphere is ionized. Remember what magnets do to electrical current, right? Remember what magnets do to electric current with this copper pipe. And so the geomagnetic energy is going to affect some of the ionosphere as well. And the A index gives us an average of those beats over the previous 12 K indices. And they vary from 0 to 100, which is greatly disturbed. So when we assess propagation, we want to look at the MUF and the LUF. We talked about those on the earlier projection, and they vary with time, season, the amount of solar radiation, and the geomagnetic stability. The geomagnetic stability. So the more unstable the geomagnetic forces are, the more unstable the ionosphere is. Remember, this copper pipe, as I drop the magnet through it, it's not magnetic. But as the magnet traveled through the pipe, it created an electrical field. The electrical field created a magnetic field which held the magnet up and kept it from dropping. So electricity and magnetism are interrelated when we're talking about propagation. They don't fall apart. They are together. That's why I wanted to show you this pipe, because it really solidifies it, at least in my mind, about this, the whole magnetic and electrical propagation issue.
Would that change if you had a pipe that was big?
It would, but if the magnet's too far away from the edge, then the electrical field is not big enough. So you need to have a magnet as you drop through the pipe. And after the lecture, if you don't want to come by and play with it, you're welcome to do that. But you want it close enough to the edge so that it creates an electrical field that's close enough to hold the magnet up. All right, if the maximum usable frequency drops below the lower usable frequency, you cannot get skywave propagation. Now, one way that you can see if there is propagation is to listen for the beacon stations. You know, like on 20 meters, 14.100 is a beacon station, and I'll show you some beacon information here in a minute. So we could turn the radio on to 14.100 and just listen to our radio with our antenna. And every 10 seconds, a new beacon station will come on, and they're all over the world. And so if I can hear a beacon station in the middle of Russia, then I know that I've got propagation from my station to Russia. And the beacon stations will give their call sign, and then they will give you 4 1-second DAWs. And the 1-second DAWs are 100 watts, 10 watts, 1 watt, and 1/10 of a watt. So they're constantly moving down. So you can see if you could get through, if you can hear their 1 watt frequency, their 1 watt dot, the third dot, then you know you're going to be able to communicate pretty well with that station, right?
There's an app for that.
There is. Yeah, Paul said, for those on Zoom, Paul said that there's an app for that, and I'll show you a little information about that here in a minute. The North California DX Foundation supports this international network of beacons that transmit continuously on 10 through 20 meters to help you figure out what your propagation is. Another thing that you could use would be to use reversebeacon.net. And reversebeacon.net is a series of receiving stations all around the world. And when you send a CQ call on CW or PSK31 or RIDI, when you send a CQ call or a test, TEST 84CJ, then it gets the stations that are decoding those stations will decode it and upload it to the Reverse Beacon website, and will tell you how loud they heard your signal, which is pretty cool. All right, so let's talk about solar disturbances. Well, a solar flare is a large eruption of energy and solar material from the surface of the sun. It's going to affect propagation because of changes in ionization. A coronal hole is a weak area of the sun's outer layer where ionized gas and charged particles escape the sun's magnetic field. And another thing that may cause problems is a coronal mass ejection. So they say mass, they're actually talking about physical material, not just electrons, not just UV radiation, but actual mass that gets ejected from the sun. It takes about 20 to 40 hours for that mass to reach the Earth. And when it does, it is profoundly disruptive to communication because it causes profound activation of the D layer, such that no radio signals would be able to get through the D layer. Now, the good news is that only occurs on the bright side of the Earth because it is facing the sun. Only the bright side of the Earth is affected by that mass ejection. Therefore, at nighttime, you don't have to worry about it. Does that make sense? All right. So UV and X-ray radiation from solar flares travel at the speed of light. And how fast is the speed of light? 186,000 miles per second. So it takes about 8 minutes for it to reach the Earth when the sun is giving off UV radiation. So when we walk outside today, the light that we're having, it increases D-layer ionization and absorption dramatically. So when we get these solar flares, the solar flare that we talked about, D-layer ionization dramatically increases, and it can cause a radial blackout. So we call it an SID, a sudden ionospheric disturbance. It affects the lower bands more than the higher bands. Why? Because the D layer is what's affected, and the D layer tends to absorb signals that are lower, such as 40 meters, 80 meters, and the higher frequencies tend to punch through the D layer, right? Remember that the sudden ionospheric disturbance only impacts the sunny side of the Earth, so the dark side of the Earth may be relatively unimpacted. Geomagnetic disturbances. So that's why we look at the K index and the A index. So remember, the sun is giving off this stream of particles that's called solar wind. It will take 20 to 40 hours for them to reach Earth. They increase ionization in the E layer, and they cause the aurora borealis and the aurora australis. I can't pronounce that word. The southern hemisphere aurora. And so these charged particles are what causes the aurora. And they will cause geomagnetic storms, and they can disrupt radiation, they can disrupt radio communication, but they can also, on VHF bands like 2 meters and 440 or 6 meters, they can actually improve reflection of those high frequencies, and you may get a wavering sound of VHF 2-meter propagation when you're up in the upper latitudes. So yeah, the auroras are caused by the gases flowing by the charged particles. They flow vertically down the atmosphere, guided by those magnetic fields, okay? So that's what the aurora is. And aurora propagation is present on 2 meters and 6 meters, and it may sound like a hiss or a buzz just because of the disruption of the ionosphere. But anything lower than 6 meters is not going to be transmitted because it's going to be absorbed by the D layer. But 2 meters is enough to punch through the D layer, and it may be reflected by the auroras. Okay. Okay, let's do some practice questions here. Again, you didn't know there was going to be a test, but here it is. You'll see how much you learned. What is the significance of the sunspot number with regards to HF propagation? Higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. Lower sunspot numbers generally indicate a greater probability of sporadic E propagation. A 0 sunspot number indicate radio propagation is not possible, and all of the choices are correct. Survey says A. Higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. What effect does a sudden ionospheric disturbance have on daytime ionospheric propagation on the HF radio waves? Yeah, it disrupts communication via satellite more than direct communication. It disrupts signals on lower frequencies more than those on higher frequencies. It enhances propagation on all frequencies or none. No, it's B. Remember, the lower frequencies are going to be more absorbed because of the D layer is more active. Higher frequencies may be able to punch through. Does that make sense to everybody? Approximately how long does it take increased UV and X-ray radiation from solar flares to affect propagation on the Earth? So this is moving at the speed of light, so it's going to be 8 minutes. Which of the following are least reliable for long-distance communication during periods of low solar activity. During low solar activity. So the sunspot number is low. We're going to have, very bad propagation on the higher frequencies. And if you've been doing this long enough, you know what we're talking about. Now, when the sunspots come back, 10 meters are incredible. You could have a 10-meter radio in your car. And I did that during the height of Sunspot 23 and routinely talked to Japan on my way to work in the morning. Pretty cool. Okay, what is the solar flux index? A measure of highest frequency that is useful for ionospheric propagation, a count of sunspots, which is adjusted for solar emission, another name for the American sunspot cycle, or a measure of solar radiation at 10.7 centimeter wavelength.
D.
Bingo, D. What is a geomagnetic storm? It's a temporary disturbance in the Earth's magnetosphere. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? Well, remember, 20 meters we can use almost at any point in time. I got to tell you a funny story. Probably 15, 20 years ago, Myron W4UR was talking to a new ham about HF propagation. He was going, yeah, that whole 20-meter band, I think that's just I think that's overplayed. It's just, it's not much to the 20-meter band. The poor guy was going, really? So Myron, stop telling that guy that. All right. Which of the following effects can a geomagnetic storm have on radio propagation? Improved high latitude HF propagation, degraded high latitude HF propagation, improved ground wave propagation, or improved chances of UHF ducting. All right, degraded high latitude HF propagation. And what effect does a high sunspot number have on radio communication? C?
C.
Yep, C. What causes HF propagation conditions to vary periodically in a 28-day cycle? Yeah, the sun's rotation on its axis every 28 days. Approximately how long is the typical sunspot cycle? 11 long years. 11 long years. What causes the K? What does the K index indicate? The K index. Remember, it's the short-term stability of the Earth's magnetic field measured every 3 hours. What does the A index indicate? It's the long-term stability of the magnetic field. So the K index is short-term, every 3 hours. A index is the last 12 K indices averaged. How are radio communications usually affected by the charged particles that reach the Earth from solar coronal holes? Yeah, HF communications are disturbed. Why? That D layer, that darn D layer becomes more active. Now, it won't happen on the dark side of the Earth, though, will it? Only on the sun, the illuminated side of the Earth. How long does it take charged particles from the coronal mass ejection to affect radio propagation on the Earth? This is coronal mass ejection.
20 to 40 hours.
Yes, 20 to 40 hours. This is not moving at the speed of light. It's moving slower than the speed of light. What is a possible benefit to radio communication resulting from periods of high geomagnetic activity? So high geomagnetic activity increases the auroras. So you may get reflection of VHF signals. In fact, is Al here? Al here? You're here. Have you bounced your radio off of the aurora?
Oh, anytime, yeah.
And so when you bounce it off the aurora, you say you want to talk from somebody here, to somebody in Knoxville, you may aim your antenna to the north and have them aim it to the north, so you both bounce off of the same aurora, right?
Yeah, but it could go at a big aurora, talk as far south as South Texas.
So yeah, Al said is on a big aurora, he's talked as far south as South Texas. So anyway, you can talk, and it's kind of interesting. It's really cool when you get VHF signals reflected. All right, which of the following applies when selecting a frequency for lowest attenuation when transmitting on HF? So I want to have the least amount of absorption. So attenuation would mean absorption. So do I want a frequency just below the MUF, just above the LUF, just below the critical frequency, or just above the critical frequency? Well, if I do it above the critical frequency, I'm not going to get skywave propagation, so D is out. If I use it just above the lowest usable frequency, then I'm going to get some of my signal to go through the D layer, but not all of it. If I use it just below the MUF, then I'm going to have the best penetration of the D layer, but still have reflection off of the F layer. So A is probably the correct answer. And in fact, for the longest communication, you do want to go just below the maximum usable frequency. So I'm going to show you some propagation prediction software here in a minute. And if I want to talk to my friend Jose in Spain, and it tells me that the maximum usable frequency is 11 megahertz, then I'm not going to be able to talk to him on 20 meters or 14 megahertz, but I would go to 30 meter band, 20 to 10 megahertz, okay? And I'd rather do that than on 40 megahertz, because that will give me the best likelihood of making a communication between here and Spain. What is a reliable way to determine if the MUF is high enough to support skip propagation between your station and a distant station on frequencies between 14 and 30 megahertz? Remember the North California DX Foundation? Let's listen for signals on the International Beacon. What usually happens to radio waves with frequencies below the lowest usable frequency? So if they're below the lowest usable frequency, they are completely absorbed by the darn D layer. So you can't say D layer without putting darn in front of it, okay? It's got to be the darn D layer. What does LUF stand for? Yeah. What does MUF stand for? B, the maximum usable frequency. What happens to HF propagation when the LUF exceeds the MUF?
Bad news.
Yeah, bad news. No HF communication over skywave between those points. What factor or factors affects the MUF?
All of these choices.
Yes, exactly. All of those choices are correct. All right, let me pull up one last one here. And we're going to talk about another mode of propagation. And that is going to be scatter modes. So now we'll talk about scatter modes. Okay, so scatter modes. Scatter characteristics are not very efficient. They tend to spread out my signal, and they deliver only a fraction of the signal strength to the receiving station. And because they're being scattered, they tend to have a fluttering or wavering sound, and they may arrive from different directions, resulting in multipath interference. they can be heard from stations that are too far away to be received by ground wave propagation, but are too short to be listened to by skywave propagation. And this occurs because backscatter results in some of the signal being reflected backwards into the so-called skip zone. And so this is a good example of what I'm talking about. So here's a transmitting station here. Here is the receiving station here. I'm sorry, here's the receiving station. So here's the transmitting station. Here's the receiving station. The ground wave propagation only goes out to this level. Skywave propagation is going to go out to this level. When I get higher than this, I'm at the critical angle and my signals are not going to be reflected by the F2 layer, okay? So this station is in my skip zone. So let's say that I'm here in Nashville and I'm on 20 meters and there's a station in Washington State that can hear me perfectly well. But a station in Oklahoma can't hear me at all. So there's a really loud station putting out 1,500 watts on the west side of Oklahoma, and he's talking with somebody in Japan. And I've had in a QSO with a station in Seattle, Washington, and he may not hear me at all, and I may not hear him at all, but he may interfere with the station I'm talking to in Seattle because he is in my skip zone and I'm in his skip zone, okay? Does that make sense? That's one thing to keep in mind, that you can have be on a frequency that you think is open and yet it's not open because somebody's been using it and they're in your skip zone. So here I am in Nashville. Here's the station in Seattle. Here's the station in Oklahoma, and we're in the skip zone. So the station in Seattle is talking to me, coming back. And what if he wants to talk to the station in Oklahoma? Well, you may get some scatter reflections of these signals from different layers of the ionosphere, but it's not going to be near as much. You sort of get reflection. It's almost like if I have a really bright flashlight and I point the bright flashlight and I've got that really bright spot, but then there's a little bit of penumbra off to the side. And so that's sort of like, if you think of it, sort of like the penumbra of a spotlight, right? It doesn't really light it up, but it's enough that there's reflection from where it's hitting the place that you can see around the area. Does that make sense? So skip zone occurs between the ground wave propagation area and skywave propagation. The reflections come back. They're scattered over a 200 to 300 mile range around the transmitting station. And one thing we talk about is near vertical incidence skywave. So near vertical incidence skywave occurs when we put a dipole antenna up about an eighth of a wavelength above the Earth, so that most of our signal is going to go straight up. And it goes straight up and it will be reflected in an area just around where my transmission site is. And it's going to be important because remember, the critical frequency is usually going to be below 7 megahertz. So if I go much above 7 megahertz straight up, it's going to punch right through the ionosphere. Depending upon the degree of ionization, the critical frequency may be like 5 megahertz. So if the critical frequency is 5 megahertz for my position, anything above 5 megahertz that I send straight up is not going to be reflected. So if I try to use Nvis on 7 megahertz, but the critical frequency is 5 megahertz, I'm not getting Nvis propagation. Nvis is near vertical incidence skywave. And so near vertical incidence, let's imagine that there is a cloud layer at 2,000 feet above the Earth. So we've got the clouds, and we're out at the state fair, and the guy's got this huge spotlight out at the state fair, and he aims it straight up at the clouds. Well, that's going to highlight the clouds, it's going to light the clouds, and we're going to get some of that reflection down to the Earth. That's the same thing that near vertical incidence skywave propagation does. We send our radio waves straight up and let it reflect in an area around our radio. and it usually goes around 100 to 200-mile radius. It works only at 40 meters and low, because when you get, what happens when I go, I was listed on the repeater several years ago, and I heard guys talking about putting an NVIS antenna up for 20 meters. And I was just shaking my head. So you're not going to use NVIS for 20 meters. Why does a 20-meter NVIS not work? Frequency is too high and it punches straight through the atmosphere. Now, they may have been able to hear each other 20 miles apart on 20 meters, but it wasn't NVIS. What was it? Ground wave, exactly. So NVIS only works at 40 meters and less. That's why it works like on 80 meters. You can get 80-meter NVIS propagation. So somewhere between 80 and 40 meters, 80, 40, and 60 meters, you can get NVIS propagation. The antenna is between a tenth and a quarter of a wavelength above the ground. So on 80 meters, your antenna is going to be 24 feet above the ground for NVIS. Now, why is NVIS important? Well, let's suppose you want to talk the same way that you would use a repeater. Normally, you would put a repeater at the top of a mountain and then use that for direct line of sight communication. It would be at the highest site, at the highest spot, and it would reflect your signal all around the mountain. But let's suppose you're in the military and you don't have the high ground. So you don't have the high ground, but the enemy does. So you may want to use NVIS to talk to all of your troops in the area all around that until you capture the high ground. Or you may have a natural disaster and the roads are all frozen and you can't get up to the repeater site on top of the mountain and the electricity is down to it. So then you may use NVIS to bounce off the ionosphere and use the ionosphere as the high point, right? Does that make sense? So here's a good example of NVIS. All right, some practice questions. What is a characteristic of HF scatter signals? They have high intelligibility, a wavering sound, very large swings in signal strength, or all of the above. Yep, they have a wavering sound. What makes HF scatter often sound distorted? Scattered into the skip zones through several different radio paths. Why are HF scatter signals in the skip zone usually weak?
Only a small amount.
Yep, only a small amount of the energy is scattered into the skip zone. What type of propagation allows a signal to be detected at a distance too far for ground wave propagation, but too near for normal skywave propagation?
Scatter.
Yep, scatter. Which of the following might be an indication for signals heard on the HF band are being received via scatter propagation? This one you got to think about.
B.
Give Hoop a cigar. That's right. So the maximum usable frequency is dependent upon the position of the two sites. So the maximum usable frequency between me and Oklahoma City may be 7 megahertz. But on 14 megahertz, he's able to hear me because he's hearing me by scatter. Even though my 14 megahertz signal will bounce all the way over him, he's getting some backscatter. Does that make sense? Which of the following antenna types will be most effective for skip communication on 40 meters during the day? For skip communication during the day on 40 meters. So I'm going to want NVIS, right? So NVIS is a horizontal dipole placed between an eighth and a quarter wavelength above the ground, right? What is NVIS skywave propagation? Yep, B. Short distance, medium frequency, or high frequency propagation using high elevation angles. Okay, so let me Let me close this down and show you a couple of other things. Okay, so in QST, QST has the propagation software here. Tomas Hood, NW7US, does this propagation. This was a pretty interesting article in 2008, and he was using a program called ACE HF right here, ACE HF for Windows machines, and he was looking at propagation between Iceland and Florida. And then this program takes a look at propagation and propagation predictions. His QTH is up here in Washington State, right here. Let me so his QTH is up here in Washington State, and this outlines the footprint of where a 1 watt CW signal is going to be heard from his station using an isotropic antenna during July of 2009. Okay, now there's a reason I wanted to show this. So this is a picture of his propagation where his station can be heard using 1 watt CW in 2009, no gain isotropic antenna. Guess what this is? This is the footprint using 100 watt sideband. So this is where it can be heard 100 watt sideband. This is 1 watt CW. Pretty interesting, isn't it? Yeah. Okay. So let me show you a couple of other.
That was a plug, by the way.
It was. Guilty. Okay, so let me share my whole screen here with you. Desktop 1, share. Okay, so here is a, this is a program that is called DX Toolbox for, this is a Windows program. Let's see, how do I move this down here? Okay. So let's say I want to look at different, and this is all the information. So I could take a look at beacons and tell it that I want to see, didn't load the beacons in, okay. I could look at a gray line map. Y'all asked about the gray line. Here's the current gray line. This is where we're at. And you can see where the gray line is right now. So as time moves on, this would move on. Oh, now here I can bring the beacons up here. Let's say I want to look at the beacons at 14100. Now this shows me currently this Israeli beacon. Here's a Finnish beacon, and every 10 seconds these beacons are going to move. And after the meeting, we may go in and turn the radio on to 14100 and see what we can hear. But if you turn this on and turn your radio to 14.100, so here's an Argentinian station. And again, they're going to send their call sign and then 4 1-second dashes, 100 watts, 10 watts, 1 watt, and 1/10 of a watt. And so you can tell there's a Peruvian station. You can tell. So if I'm turning the radio on and I'm listening on 14100 and suddenly I hear beacons right now at this point, then I know I'm going to got communication between me and him in Venezuela. Okay. So let's say I want to predict what my MUF to LUF calculator is. So here right now, I want to go from here, and let's say I want to go to Spain, talk to my friend Jose. So this is my home latitude and longitude. So we'll go down here to Spain. So I want to look at the pathway between my home at this latitude and longitude in Spain, which is this latitude and longitude. And right now, we're 1500 Zulu. So I can see what the MUF and the LUF is, where I've got propagation, okay? So looks like the LUF right now between hertz, and the LUF is there, and the MUF is going to be like 3,400 megahertz. So if I want to talk from here to Spain, I'd probably pick 10 meters right now. Does that make sense? Using 100-watt power with this solar flux. So this pulled up the solar flux from the current information. Also, let me show you on QRZ. So when you go to QRZ.com, okay. So right here is the current solar information. So you see here, it gives me the solar flux index of 343, the sunspot number of 99, the A index of 6, the K index of 1. Move out to the side. So you've got all the, and then down underneath it, it shows you which bands are good. Got a delay here. There you are. So it shows you which bands are good at night and during the day. So all this is right present on QRZ.com. Okay, so let's go back. Let me pull up this propagation stuff again. Okay, let's go with calculator. Let's take a look at propagation for time between me and Jose. So I'm going to go between me and Spain again. So for right now, it looks like the lowest frequency I could use would probably be in the 17 meter band. Probably the 15 meter band would work good, but my best propagation is going to be probably on this time with this solar flux between me and Spain. What about if I go and talk to Australia right now? All right, let's take a look. I'd have to be on 10 meters to get from here to Australia. How about Cuba? Between me and Cuba, there you are. So my right now I could probably get 15 meters between me and Cuba pretty well. Does that make sense? Any questions about any of this? Well, thank you all for your attention. I appreciate it.